Welcome back to the series. Last time we calculated the correct parameters for a transformer and installed a new transformer. I'm testing it now by measuring the voltage on top of the bulk capacitor, and look at that, it's oscillating around 22 volts, just as we calculated, just as we predicted. So that problem is sorted now. Then I proceeded to test the board, turning it on and off a few times, and at some point it stopped working. I think the ripple just moved some chip that was already on the edge of it and moved it over the edge, and it failed. So now I have to troubleshoot the board before going back to the ripple, and to do that I'm going to socket the entire board. Let me tell you why. Here are the reasons I want to completely socket this board. First of all, it could be that there are chips or tantalum capacitors on the board that are contributing to the ripple in the power distribution network, or the PDN. It could be that some of those chips, even if they are actually working logically, they are electrically compromised. There can be a very low, for instance, a very low impedance from VCC to ground on that chip. And that can contribute to increasing the ripple. That could be actually a cause of ripple if you have an electrically compromised component. Could be a chip, it could be a tantalum capacitor. I need to change those tantalum capacitors anyway, because probably a large number of them is not good anymore. That's the first reason to socket the entire board. The second one is to spare these very old fragile chips from back in the late 70s. By socketing the board, I can replace them with new ones or new old stock ones and submit those new ones to the stress of testing this board, including the ripple that's currently present. It probably already ruined one of the chips. I don't want it to ruin the other old chips, so I want to spare them, and socketing the board contributes to that, enables that even. And the third one is the long-term maintainability of this board, which actually is two boards connected together by a number of bodges. I don't want people to have to keep on flipping this board up and down to maintain the computer going forward. I want to make the work and the job of the next conservator after me 40 years from now a lot easier than my job was. And socketing the board prevents the need to desolder things when they go bad in the future. And finally, there is the bonus, which is if everything is socketed, it's much easier to identify the defective chip. It's much easier to take the chip and do an offline test with a tester, as opposed to trying to trace something with an oscilloscope. So these are the reasons. Now, desoldering everything from a board can be very stressful to the board. This board is fragile. I could see that some pads were trying to get the glue detached. So I'm going to use the right tools for this. I pulled out the Hakko FR410. It's a much stronger desoldering station than the one you've seen me use before. I try to use the same tools that every hobbyist has access to, but in this case it would be irresponsible. This tool, this desoldering station, has a much stronger pump. You do not need to dwell long on any pad. You do not need to wiggle around the pad, which can be mechanically stressful. Things just come off and just need to do one more pass very quickly with a desoldering braid. So I desoldered every chip, and I also desoldered and replaced every tantalum capacitor. I tested them, and about 1/3 of them were just downright bad. The ESR was way too high, they wouldn't be working well. And of the 2/3 that passed, about half were marginal. So none was completely shortcut, but they were not okay. So they needed to be replaced anyway. I replaced them all, hoping that all of this could reduce the ripple. You know, I tested the board, and you're about to see I'll be testing the board with no chips in it, only the new tantalum capacitors in yellow that you can see there. And when I turned it on with almost no load, there was still a lot of switching noise, as you will see in a moment. I added some chips to increase the load a little bit, because the switching noise, the ripple can decrease with a little load, but it didn't do anything. It just increased the ripple, just increased the switching noise that you can see there. So the problem was not in the capacitors, the problem was not in the chips. The problem is in the power supply itself. The power supply is not good. It just inherently has a lot of ripple. And I'll have to deal with it later, but for now I want to concentrate on getting the board functional again. It's a psychological thing. I should deal with the ripple first. But yeah, I'm eager to see the DAI PC prompt again. So all the chips that I've desoldered, I've cleaned their pins, both with a fiberglass pen and with a contact cleaner. I've straightened all the pins again, and I've tested them one by one on my tester, which is what I'm showing you now. This is a 107. Every chip will pass except one of the custom PROMs, one of the custom programmable ROMs that the DAI used in lieu of logic chips, used in the form of lookup tables. I'll show that in a moment. But all the other chips just passed, as that one that you just saw. We tested the memories in an earlier episode. They are all working. I tested them again just to make sure they are all working. And there you see a fully socketed board. Most of the chips you see now are brand new or new old stock because I didn't want to stress the old chips. I also took the opportunity and changed, I think there were 6 or 7 transistors on this board. They were all okay. When I removed them, I tested them, they were all okay. But I had brand new brand new units of the same parts. So I thought I'm not going to put the old stressed ones here. This is a very discreet update that can go a long way in improving the future of this machine. Now there was one chip that you can see there to the lower left. It was getting very, very hot on the infrared. And that's one of the PROMs, one of the custom programmable ROMs that play the role of logic. I think there are 6 of them on this machine. And when I tested it, sure enough, it was bad. Now I have a bunch of blank old ROMs. That's the 74S287. I have a bunch of blank ones because I expect to be repairing more DAIs in the future. So here you see me programming a new blank to replace the defective ROM. If you are in the world of DAIs, the defective ROM was the white spot PROM, I mean. These are essentially custom chips, so you have to have the old ones to replace them. There you go, that's a 74S287. Or you have to make a version using a modern PAL or PLA or PLD. That's possible. I actually did it. I'm not going to show it in this series, but I actually did it. Now I will be loading in a moment the binary file that corresponds to the correct white spot PROM. There we go, white PROM. I will be loading that, and I will compare that to what I read from the defective PROM. So you see the difference. You see on the white screen, you see the contents that are the correct ones, and on the black window, you see the ones I read out. And from address 40, 50, and 60 in X, you see lots of zeros when there should be content there. You see line 40, line 50, and line 60. There's a lot of stuff there, but in the defective PROM, it was gone. So it was really bad, not only because it was hot, but because it didn't hold the right contents. So now I'm going to blank check the new S287 that I put in there. So it's indeed blank. My supplier was honest. I bought these chips from someone in Greece, and they are very reliable. They were a very reliable supplier. Now I have programmed it with the correct PROM contents, and I would test it a couple of times to verify it, just to make sure that it is correctly programmed. These are very rare parts to find unprogrammed. You can see advertisements in China, but probably they are programmed and there's nothing you can do about those. I got lucky to get a batch of 287s and 288s that were unprogrammed. So there goes the new chip in, the new PROM, in the position of the white spot. I'm going to put a heatsink later on because it's an old part. It does get hot still. Something else I did was to refurbish the black and white video card. I only have a black and I actually have a color card, but it's not working. In this series, I'll keep this computer as it was. So I'll just refurbish this black and white card. I changed the transistors. One of them was a little noisy. I changed the capacitors as well. And I replaced the cables with some handmade twisted pair to keep the video signal sort of clean. and I implemented the composite mod on the RCA connector of the modulator CAN as opposed to a separate RCA connector, so there's no confusion now. And then it still didn't work. Without the new chips, everything tested, but I found the reason very quickly. Can you see that bent pin wrongly inserted? And then I corrected that, but it still didn't work. And with the oscilloscope, I traced the problem to this chip, the 74123 pulse generator. I had put a brand new part in there, a brand new 123, but it wouldn't oscillate, it wouldn't generate pulses. Only the old chip would work, even though the new chip was identical. So what's going on here? We need to understand this. This part of the circuit, it's worthwhile to look at it at the schematics. It's not complicated, but it's important to have an overview so you can follow what's about to happen. This is basically a pulse generator. You have here a register. I believe it holds an address value. And one of the bits of this address, one of the higher order bits, is used as an input to these two pulse generators. The two pulse generators are part of the same chip, IC111, which is a 74LS123. It's the same here, 74LS123, which is a pulse generator. What it does is when this input signal has a transition, let's say a falling edge, you have the same thing here, of course, because it's the same signal. Every time there is this transition on the input, here on the output, there is a Q output here and a Q bar, which is the negated version. Same thing here, Q and the Q bar here. On the output, you will produce a pulse with a certain pulse width. So let's suppose this is pulse width T prime, which is this distance here between the two edges of the pulse. Same thing will be here, but the width will be different. I'll tell you in a minute why. Let's say this is prime prime, and the width is this distance here that determines how long the pulse is. Now, every time there is this transition on the input, you get a pulse with a certain duration at the output, and the duration will be given by this external capacitor and external resistor, which are connected to the 5-volt rail. The higher the resistance and the capacitance, the longer the period or the width T of the pulse will be. In this case here, there is only a resistor and no capacitor. I can tell you this will not work without some capacitance, but what DAI was doing is they were using the internal parasitic capacitance of the chip and the external parasitic capacitance of the board itself. Even if you don't put a capacitor, there is always some parasitic capacitance inside on the chip and outside on the board. That's what they were counting on. They wanted a very narrow pulse width here. Actually, we even have the value here, 50 nanoseconds. Here it's a much longer one, 250 nanoseconds. That's why you have the external capacitor and a much larger resistor. But to get a narrow one, you want a smaller resistor and a smaller capacitor. And in this case, they went as small as they could possibly go. Now, in this case, this pulse, or the negative version of this pulse, which also has 15 nanosecond duration, it goes into the clock of a flip-flop. The input D of the flip-flop is connected to 5 volts. So when the clock toggles, D goes to Q. And the inverted version of D, which is ground, goes to Q bar. And here you have, I think that's the clear input. That's how you get different values. Either you toggle the flip-flop or you clear it. And then the output, you just invert it using an OR gate. You know, if you OR something with itself, the output is the same, but then it's inverted. So this is an inverter. There is another inverter here. This is a simple voltage divider. Actually, this is wrong. This is connected to 5 volt. Plus 5. That's what is actually on the board. The schematics are wrong in this regard. So you get a voltage divider and then your column address select for the DRAM. And that's the whole point. You want to generate the CAS and the RAS signal to read and write to the DRAM, RAS being the row address select. That's what the whole point of this thing is. And then you have some more conditioning logic here, some passives, a diode for some voltage drop or some feedback. They are just shaping the signal electrically the way they want it to look like, so the DRAMs recognize the CAS. Same thing for the RAS. It's also shaped by some external circuitry here. Now, this shaping circuit here at the end of this second pulse generator, the way it's on the schematics, I understand it. You're biasing this transistor here in such a way as to give you the correct shape. The emitter is connected to 5 volts to drive it. Then you have a AC feedback loop through this capacitor. This capacitor here will prevent any DC charge from going back to the base, so you don't get a DC feedback. This is purely AC, probably to, I don't know, remove some oscillations, filtering. You have a resistor here that allows you to control the voltage that you get at the base of the resistor, and also limits the current that flows. And then on the collector side, you have a voltage divider, and you double drive it, because you're also driving it with the inverse of the signal that goes into the base. So if in the base you are in the positive cycle, here on the collector you're in the negative cycle. So one pushes, the other one pulls. And the same thing the other way around. When the base is on a negative cycle, the collector will be on a positive cycle. And again, you will push and pull, but just the other way around. And then you get a voltage divider, and that's your RAS signal. I understand this. Now, there are several problems with everything I just told you. Let's begin from where we just were. This is what is on the schematics. Both the dynamic club schematics and the official schematics from DAI. But what is on the board is this. You have this extra connection here, which closes a DC loop, which is strange. You just biased your resistor, your transistor in such a way that there is a DC cycle there. So what is this transistor doing? Now it could still play a role, but it's not very intuitive. I'm not sure why you would do things this way. This capacitor now is completely in parallel with the first resistor. R139 is completely in parallel with that capacitor. This is not what I would think about if I were designing this for the purposes they use this. It's not the way I would think about that. And I even, at some point, I cut this connection on my board. You need to cut 2 traces to remove this connection, because there's a double connection there. And I cut it because I thought, I don't understand this. What I do understand is this. This I understand. So I cut this, but as you will see in a video shortly, this will not work. And I think I know why this will not work. Here's what I think might have happened. Of course, I'm not sure, but here's what I think might have happened. They prototyped this entire circuit here, either on a breadboard or on a wire wrap setup. And when you are, connecting jumpers or wrapping wires, it's very, very easy for you to add this connection without meaning to add it. The way the circuit is set up. You know that there is a feedback line that comes here. You just put it too early. You just connected it to the wrong side of the capacitor. This is what you want. But if you connect it on the wrong side of the capacitor, this is what you get. And then after they did that, they still did that because they were going through their list. I think this is what happened. They added this in their prototype by mistake. And then they proceeded to calculate the values of the passives, not through true calculation, but through estimating with, as we say in the Netherlands, or with a finger in the air. You estimate what these values in principle should be, more or less, order of magnitude. And then you start testing different values on your prototype to see what precise values actually work, instead of going through PSpice simulations and all that back at that time in the late 70s. there was very little of that, and then you'd have to run some equations, which are not complicated, but I can see engineers doing what I'm telling you, just trying out different values. I did that at university, and I got caught. That's how teachers get you when you are when you are doing your bachelor's in electronics engineering. Now, you empirically define these values here, and you can always claim it works, but and then your teacher finds something like this, and your teacher will know you didn't calculate anything. You just tried it. I got caught like this once. So it's not beyond the realm of possibilities that this is what has been done. And then, if you try then to remove this, it will not work, because all the values were calibrated based on the existence of that DC loop that was there. The whole thing will not work. And lo and behold, as you're going to see in the video as we continue, I had to put this connection back because it would not work without it. There are other problems. Here, there should be a capacitor here, which DAI didn't put. Why? Because they were counting on a fairly significant internal parasitic capacitance inside the chip itself, and maybe some on the board. They were counting on those, and they wanted a very narrow pulse here, only 50 nanoseconds, as you see here, which is pretty short. So what they did is they dropped the capacitor, assuming that this is there. And then the resistor is very, very low. If this capacitance here is small, like a couple of picofarads, with the resistor that low, connected to 5 volts, you charge that capacitance instantly. And then you get no oscillation, because it will be charged instantly. You don't get oscillations like that. You don't produce a pulse at the end. So they are assuming a very large parasitic capacitance in the chip itself and on the board. Moreover, and because this value is so low, this resistor gets very hot. And if you look at the images in infrared, which I'm showing you now, this resistor, not this capacitor, this resistor was glowing hot. It gets very hot because there's a lot of current going through this. It's a small resistance. Another problem was that when I replace this pulse generator, the 74LS123, with a modern part, the same part, LS123, but recently manufactured, the internal parasitic capacitance is tiny. It's much lower than the older chips because it's a better process. You don't want parasitic capacitances. Parasitics are undesirable. And then without an external capacitor, there will be no pulse. If you put a new LS123 here, it doesn't produce a pulse at all. And that's a problem, because I want this board to be maintainable. It's already socketed. I want people to be able to just remove the 123 and put a new one if it goes defective. And the new one should also generate the correct pulse. So as you will see, I'm going to recalibrate this whole thing here for the new chip. So a new chip produces the pulse. The old chip is still working, but there are two problems with it. One, it gets too hot. And two, it's not producing the right pulse width anymore. I think it's producing a pulse that is slightly too long, if I remember. I don't quite remember. It's either too long or too short. I think it's too long. So there is a double reason to get rid of it. It has drifted over time. Pulse generators like the LS123 do drift over time, let alone 45 years. So the pulse is not coming out correctly. It's coming out too long, and it gets distorted because the next pulse is supposed to start before the previous one ended. And then what you get is something like this. You get everything very distorted. You don't get a properly formed pulse that goes all the way down and then the next one. You don't get that. Now, to use the new one, I will change the value of this resistor. In a moment, I'll show you what I used in the datasheet as a guide to change this value, but ultimately, I empirically experimented with a couple of different values on the PCB itself to make sure. In this case here, there's another problem. The pulse coming out at the end here is also skewed, has also drifted. It's also a little bit too large. So I changed the value of this resistor here. And I slightly calibrated it also for the new 123. It's the same chip. The same chip has these two oscillators. or pulse generators. I'll change this value as well, or I have, and I'll show you in a minute on the datasheet how I chose the new value. With the old chip in, I do get oscillations, as you can see, but the pulses are malformed. They overlap one another. That's the 50 nanosecond one. The 250 nanosecond is also malformed, as you can see there. So the old chip has failed. It's still oscillating but doesn't produce the correct pulses. And it indeed was getting very hot on the infrared at the bottom of the screen. You can see that it's very hot. To the left there is another hot chip, but that's a PROM. I expected it to be hot, not the pulse generator. So I replaced it with a brand new LS123 and I put new passives around it to get it to oscillate. I will share with you how I came to these values shortly, but I do get proper pulses, as you can see on the oscilloscope right now. So this is the sweet spot, a new 1, 2, 3 and new passive values. On the datasheet of the pulse generator, or the multi-vibrator mono, I forgot the name, the official name, it's a pulse generator, the 74LS123, you find this figure here, figure 4. This is the one you want. If you don't want to calculate much and just look at pictures, that's the one you want. And here, for this circuit here, in which you have the external resistor and the external capacitor, and that goes into the two inputs of the pulse generator. The way you calculate these values, or you choose these values, the resistor in ohms and the capacitor in farads, is you can look at this picture. Here in the horizontal, you have the capacitance of the external capacitor, Cx, which is this guy here. And here on the vertical, you have the pulse duration. And remember, the pulse is something like this. And the duration is the width t of this pulse. You also produce the negative version of the pulse in the other pin, which has the same duration. And then for different values of the external resistor, RT, which is this guy here, you can see for what you will get, given a certain capacitance, what you will get for that resistance in the output width. Now remember, in one of the cases we wanted 50 nanoseconds, which is right here, right about here. So that's the curve that gives you, with minimal external capacitance, say 1 picofarad, external or internal. So I think the parasitic capacitance here would be in this area here, 1 to 3, maybe 4 picofarads, unlikely to be 4 with a modern chip. Let's say around 2, around here. So if you take an external resistor of 5 kilo ohms, which is this line here, you will get it. Now, to be more compliant with the old design, I picked the lowest external resistor I could that would still give me an oscillation and would still be around 50 nanoseconds. So I think I picked something right below 5 kilo ohms. I'll put on the screen what is the value that I ended up putting there. I don't remember as I am narrating it, but it's on the screen right now. And for the other one, we wanted 250, which was around here. So you just see what you do. Let's say we take 100 picofarads. So you just go up on this line. And let's see where the line meets. Meets around here, which is around 5.6. But I think I chose something slightly lower by calibrating on the board itself. So here DAI chose correctly. They chose 5.6 instead of 5, but 5.6 is the closest value above 5. I picked, I think, 4.7. I'll put it on the screen. I picked a value just below because of the parasitics. I was taking into account the parasitics and I calibrated it on the actual board with the modern LS123. So to take into account what we have today. So I picked a value just below that and I kept the 100 picofarad capacitor. That's what I did. And the result is perfectly timed pulses. This is the 50 nanosecond one. I'm measuring 55, but that's measurement error. It's a very nice pulse. And the 250 nanosecond one, I'm measuring 255, but that's also a rounding error. It's a very nice pulse. So now we have a fully socketed board with the old chips back, except for the ones that were bad. I'm powering it with my bench power supply for the 5-volt rail, and it's back to life. The DAI is alive again. And as you can see, the screen image is very stable because I'm using my bench power supply. You see 8.5 volts there, but that's just to take into account the loss on the leads. I'm getting 5 volts on the board, so that's correct. It's working again. Now we still have the ripple to deal with. All right, let me try to give you a summary of what I've done in this restoration. I'll be honest with you, this has at times been a very frustrating restoration, because when you're restoring a machine, usually you are bringing a proven design back into working order, but this was probably factory refused. This was a non-working board. The keyboard part is obviously, it was not working, that's why it was cut out, sawed away and replaced with this. The power supply it's a nut job, and there were things in the logic like the circuit for the pulse generators here that just didn't make sense. I even cut some traces here and brought it back to a state that made sense. But because of the way everything else around it was designed, which was probably by trial and error, it wanted it to be the way it was before, that funny design, which I bet with you, I think I know how this happened. I think what happened here is that this probably was a computer designed by mathematicians, people very good in logic design, but with no idea of electrical design. And when they were designing the timing circuit using this pulse generator here, or this multi-vibrator, I think is the official name, they probably prototyped this with wire wrap. And they probably started testing out different values of the passives around it to see what worked. And somebody hit upon a circuit configuration that didn't make much sense, but worked, and they stuck to it. And that's how we got here. It is not a design based on calculation, but it's an empirical design. It's based on trial and error, which is not the way you do things, because you have no idea what the margins are. And you have no idea what you're taking into account unknowingly into the design. For instance, you may be taking into account a particular air humidity value and temperature, and a particular pattern of EMI, electromagnetic interference in your environment. Anyway, I put it back using 2 bodges, one here and one here, to how it was, even though it didn't make sense because it worked. I did change the value of this resistor here, this and this resistor here, because with the values that were here, which just didn't make sense, a new pulse generator, I am using a new one because the old one was getting way too hot. It was burning hot, and I didn't want to calculate values for these 2 replacement parts based on the particular parasitics of that 45-year-old part. So I calibrated it for the new part. I replaced it with a new one. I also replaced this register here with a new one. The old one was working, but it was not driving the output lines strong enough. It was under 4 volts. This one drives the output lines at more than 4 volts, even though it's an LS family as well. So I replaced this. The old one was working, but it was getting too hot and was not reliable. So I replaced this one, recalibrated the passives around the pulse generator for this new part, replaced this one. Then I replaced these 2 bus drivers here, because the old ones, although they were working logically, they were also not driving the output lines hard enough. I'm keeping the original memories, even though their values or the program in them doesn't match the reference I have from the internet. I think this was first version code. This is a very, very early machine. This was a non-working prototype that probably was thrown away by the factory, and some in-data engineer picked it up and figured that they could hack it into working order and save, I don't know, it cost a lot of money back in the day. In the case of the memories, I think it's very early code, and now I understand why the memories are piggybacking. There are two identical chips piggybacking on one another for all three, you see? And all pins are connected together, so this is not for memory expansion. This makes no sense from a logical perspective, but I understand it now. The bus design, the electrical bus design of the board is so bad that a single chip doesn't drive the data bus hard enough for the machine to work. And that's why what I imagine to have been an in-data engineer that picked this up from the trash, that's why he put two chips on top of one another to drive the data bus harder. And I know this was necessary because when I replaced these memories with my own, I can show you here. See, I have those replacements, and I have 3 replacements with modern technology that doesn't work very well, and I have 3 replacements using a 2764, which is old technology, also doesn't work very well. So you actually need to drive it very hard with 2 chips. So I read out the contents of these memories, so it's safe. I can always burn 2 EEPROMs per socket here and drive it equally hard, but I'll keep the original. I'm trying to keep as much of the original as possible. So these 2 chips were changed. Everything else is original except for the PROM. This PROM in here with a heatsink. That PROM, I burned a new one. I happen to have a bunch of blank chips for all these PROMs. When you see chips with these little heat sinks, they are the custom PROMs. And this is just a timing generator for the video circuit, but it also gets very hot. And this is the clock generator for the 8080A. It gets very hot as well. Both are original chips. I just put heat sinks to conserve them. And everything else with a heatsink are these custom PROMs that I can replace, but I only replaced the one down here that was defective. I added this bulk capacitor for 1700 microfarad to reduce the ripple. The ripple was beyond 600 millivolts peak to peak, which is absolutely ridiculous. Now it's under 300 millivolts, which is still ridiculous. It should be under 50 millivolts, but at least a little better. I can't just keep on adding filter capacitors indefinitely, because when you turn the machine on, there is a current inrush to charge the capacitors. So the impedance of the power distribution network when you turn the machine on is basically 0, because the capacitors are being charged and the only resistance you have are through the traces. And as we've seen in a previous episode, this power supply, even though it uses a switching controller that has provisions for current limitation, in-data didn't use it. They just grounded all 4 pins that were meant for a current limiting circuit using some passives around. So there is no output current limitation. If I put too many filter capacitors, it will suck in a lot of current when you turn the machine on. And although I put a switching transistor here, a pass transistor, that is very robust and oversized, I still don't want to add more capacitances indefinitely. I also added 150 micro here discretely, a black radial capacitor, an axial capacitor, red and gray, that looks like a chip, so it's inconspicuous. And I've changed these 2. They were 1 microfarad tantalum capacitors before. Now they are, I believe, 47 microfarad tantalums, because there is very little bypassing in the 5-volt rail. All of these bypass capacitors here are in the 12 and the -5 volt rails, which are based on linear regulators. So I don't know why the in-data engineers put so much bypassing for the regulated voltage rails, linearly regulated, which have very little ripple. But for the major 5-volt rail that comes through here, they put only 1 microfarad little tantalum capacitors here and there. I mean, it should have been the opposite. Little bypass for the linear linearly regulated voltage rails and a lot of bypassing for the one using the switching regulator, the switching pass transistor. But yeah, it is what it is. I refurbished the black and white video card. The transistors are new. There's also a transistor here underneath the original composite video modification. I replaced that one as well. The original was a little noisy, and I put new tantalum capacitors everywhere, including underneath in there. So that should be pretty stable now. I have been using my bench power supply for the 5-volt rail to eliminate ripple, but I will of course test the machine again with 5-volt rail switching provided here, and what you will see is that in the image on the screen there will be a lot of ripple because it's still almost 300 millivolts peak to peak of ripple. You will see that in the video. The power comes through this red wire, and you will see that in the video. It's ugly, but this is how this machine is. There is only so far I can improve that without replacing the 5-volt power supply entirely with a modern switching regulator, which I may eventually do, but then I have to disconnect the pass transistor, the other transistor down here that's part of the Darlington pair. So yeah, but how far do I go? It's a trade-off. I want to keep this die as original as possible. The chips, except for the one that was defective here, plus this, and this, which were not defective, but were marginal and not working quite well, except for these 4, 5 chips, everything else is original. All the memories are original, everything is original. This is original, even the composite mod is original. It's from back in the day, not original from in-data, but original from its previous user. And I want to preserve the character of this machine, so there is only so far I can go in preserving that character and making this a robust, usable machine. To make it robust and usable, I have to basically replace the power supply. As far as the 5-volt rail is concerned, the other two are okay. And that will deface the circuit here inside. I already made a few modifications. I put an extra capacitor in here. It's a 47 microfarad tantalum capacitor that was not there originally. I already put this in there. So yeah, if I start putting another switching regulator, then it's not anymore this unique, original, very early die. And I don't want to deface it that much. So the conclusion will be, this is a die that can be turned on and demonstrated. The image on the screen will be shaky, and if you keep it on for very long every day, chips will fail because that ripple is not healthy. But you can turn it on for little demonstrations, turn it on for 10 minutes at a time now and then, and it will still be largely original. Yeah, it's completely socketed, but that doesn't make it unoriginal. It just makes it maintainable, serviceable, without anybody having to flip this board, back and forth with this loose keyboard and all these wires in here. I'm going to take out this tape and I'm going to put a little bit of hot snot for strain relief on the solder connections, but I don't want people to have to manipulate this much. That's why I socketed everything, not only to test it with new chips, but to prevent the need for anyone in the future having to desolder and flip this board and subjecting it to more stress.